Kia ora guys, this video is the last question in the AS paper from November 2021 that I gave out in class the other day, and it's paper 1-1. So what we've got here are a couple of integration problems, and the first one is what we call an improper integral, where we have to find this integral and the top limit is infinity, which feels kind of weird, right? But what we're looking at is whether, even though we've got an asymptote or something going on with a function, so let's just draw, I'm going to draw a function that is not this function. Say I've got a function that looks like this, and it's heading off to an asymptote. What I want to know is, even though it's going on forever out here, is the area under this so tiny that it converges to a finite number, right? And if you think about that for too long, your brain might start to hurt, but that's what we're doing here. These actually aren't that hard to work out as long as you're confident at dealing with this top limit of infinity. And what we're going to do is we're going to replace that infinity by b or something like b, and then at the very end we're going to look at the limit as b goes to infinity. I've put quite a lot of practice questions on this up on Google Classroom. Because this is an AS topic, I haven't had time to do it with you thoroughly in class. So go have a look at those textbook questions, they're really good. All right, then the second one is a volume of revolution question, which is not too bad. Oh, and then there's a last question that I forgot to do, right, which is this one here. Okay, we might not get to that. Right, so let's look at this first thing. We've got this improper integral, and I'll rewrite it straight away with a fractional power. So we can see that this is not too bad at all. To anti-differentiate, I'm going to rewrite it like this. This is equal to the integral between b and 1 but I need to be taking the limit as b goes to infinity. So that's just going to sit there until the very end. And I'm going to call this whole thing I for integral. So I is equal to the limit as b goes to infinity of, right, so this has to go upper power, so 3x minus 2, upper power to negative a half. I need to undo that, so I need to have a negative 2 here for when I differentiate, and I need to undo this 3 that's going to come out of my chain rule, right, so it's going to be times 1/3 here, and we've got b as our top limit and 1 as our bottom limit. So just leaving that limit as b tends to infinity sitting there, I can pull negative 2/3 out the front, and now I've got 1 over root 3x minus 2 here, and I'm evaluating it at b and 1. And so here we've got negative 2/3 times 1 over root 3b minus 2 minus 1 over root 3 minus 2, which is simply 1. So just leave that in here. We're going to have a look at this slowly in a second. And here we've got take away 1. So it's fine to do some work off to the side. So as b goes to infinity, 3b minus 2 also goes to infinity. And the square root of 3b minus 2 also goes to infinity. So that means that 1 over root 3 by b minus 2 is going to go to 0. So you can just kind of park that off to the side, right? And now we can use that result in here. So this first limit is going to be 0. And we get negative 2/3 times 0 minus 1. So my final answer is simply 2/3. All right, please email me if that's weird, and I will point you in the direction of some more practice and maybe give you a hand in class. The next question is a volume of solid one. Right, and we're told that the shaded region is bounded by the curve, the x-axis, and these lines. So we want to rotate this around the x-axis. So it's a pretty straightforward one. The volume of a solid comes from the idea that I'm getting lots and lots of disks. So it's going to be basically pi r squared done over and over and added up, right? Because you can imagine a circle here, right? That's the f of x, so that's your radius there. A circle here, a circle here. So all of these disks getting added up together. So this is going to actually be an easier integral even than the question before. And these are my limits here. Okay, so v will equal this. We've got pi, and then we've got f of x squared. Okay, right. So a bit of cleanup. We'll pull the pi through the front, and we've got 3x minus 2 to the power of negative 3 dx. Right, time to anti-differentiate. We're going to up the power by 1, and we'll get 3x minus 2 to the negative 2. We're going to undo the negative 2 when we differentiate, and we're going to undo the 3. If you're watching this from AS and this isn't making sense, let me or Mr. Hawk know, and we'll do you some easier videos on the chain rule. But we're good to go now. So these constants are going to get mucked up if we leave them sitting in there. So we're going to work with negative pi on 6 out here. And then here we've got 1 over 3x minus 2 squared, evaluated at 2 and 1. So negative pi on 6. And then substituting in 3 2's are 6. 6 minus 2 is 4, so it's 1 over 4 squared. And then 3 1's are 3. 3 minus 2 is 1, so it's 1 over 1 squared. So negative pi on 6 times, what have I got? Well, I've got 16 here, 1, 16 minus 16. Let's see, I've got negative pi on 6 times negative 15 on 16. Simplifying a few things out, we get, sorry guys, I'm trying to concentrate. I've got violin practice going on. So 15 pi on 96, and simplifying that, knock out the 3's, we get 5 pi on 32. So there you go. Right, so that's 7 minutes in. I just want to have a look at this last part and see what we've got to do. It's the first 2 bits done. I think the last bit is a differentiation question. Oh yeah, okay. So the normal to the curve at the point 1, 1 crosses the y-axis at point A. So let's try and draw that on. Let me get a ruler. So the normal to the curve, so where's the tangent to the curve at 1, 1? Right. So that's the tangent that I've drawn there. And the normal to the curve is going to be perpendicular to that. And that's what we've got to find. So there's the normal to the curve, and it crosses here. So to do this question, I have to differentiate, find the equation of the tangent, find the gradient of the tangent, the gradient of the normal, and then get the normal equation. So let's do that now. All right, so the steps that we've got to do should be pretty good. We just have to not muck up our differentiation. We're going to start with my function, which is y equals this. So work with fractional power form. So 3x minus 2 to the negative 3 over 2. First, I'm going to get the gradient of the tangent to the curve by differentiating. So it's negative 3 over 2 times this, times the 3 for the chain rule. So we get negative 9 over 2 times 3x minus 2 to the negative 5 over 2. So at x equals 1, what have I got? We've got it equal to negative 9 over 2 times 3 minus 2 to the negative 5 over 2. So that's nice because 1 to the whatever is 1. So it's negative 9 over 2. So that's the tangent gradient. The normal gradient has to multiply to give me negative 1. So gradient of normal is going to be m is equal to 2/9. So the negative reciprocal of that. So the normal equation will be y equals 2/9 x plus c. And we are looking for what the value of c is, right? Because that's going to be the thing that I'm after. And we know that 1, 1 is on the curve or on the line. So 1 is equal to 2/9 plus c. c is equal to 7/9. So there we are, we're done. We could nicely write out y equals 2/9 x plus 7/9. And then we could also nicely show that there's point A, y coordinate is 7/9. All right, thanks for watching. I think that question is probably one of the worst done in the paper. I haven't actually read the examiner's report yet, but it feels to me like there are quite a few places to go wrong in there, even though the good thing about questions like this are that it's pretty clear what you've got to do, right? There's no real problem solving in there, like seeing your way into the question, but there are a lot of steps that you've got to be very fluent with. Just especially watch with your fractional powers that you're not mucking up coefficients and that you're always checking your working back when you've finished those questions to make sure that you're not stuffing it up.